This is going to be a fun one. Now you're all going to remember every single little thing you learned in trig class. All those identities, all those graphs, it's all going to start coming back to you. So trig functions are defined differently than other types of functions, and they certainly behave differently, and the graphs look differently. So finding their derivatives is going to be a little bit of a different process, but we're gonna. So if you just think about it intuitively, think about just a sine or a cosine, think about what that graph looks like. It goes up and down and up and down and up and down in a wave-like motion. So I hope it kind of makes sense that its derivative would do the same thing. If you think about what it's doing, okay, it's speeding up and then it's getting to the top and then it's turning around and it's going back down and then it's coming back up again. So if you picture like a tangent line on a sine curve, it just keeps kind of doing the same thing over and over again. And since the function's periodic, the derivative must be periodic too. It must repeat every 2 pi. And it's like, well, what kind of functions do we know that are periodic 2 pi? Other trig functions. So that is, in fact, the case. The derivatives of trig functions are just some other trig function. So we're going to let's look at that more in depth. Let's look at the graph of sine and figure out, using what we, our powers so far, what the derivative of that we think should be. That's good old sine of x. It's the one that goes through the origin. So just kind of like we did before, where I said, okay, here's a curve, draw its derivative. We have two things we know off the bat. The first thing is, if you look at those, let's see, 1, 2, 3, 4 mins and maxes on that graph at all the pi over 2's, at those 4 points, whatever the derivative of this is, it would have to be 0. So it has to hit the x-axis at those 4 points. So those line up. And then all we have to do now is say, okay, if you look from 3 pi over 2 to negative pi over 2, the function's decreasing, which means whatever its derivative is, it must be negative in there. From negative pi over 2 to pi over 2, the function's increasing, so the derivative must be positive in there, but then switch back to being negative again. So just kind of picture that in your head before you draw it on whatever you're drawing on. Here's what the only thing it can really look like is that blue function. So that blue function is basically what the derivative should look like. And spoiler alert, it is the derivative because I know what it is. So that's the graph. So everybody at home now is going, oh, I know that graph. That's cosine, right? Cosine has the same shape as sine. It's just even, symmetrical. So we suspect, and we will do a little work to show that the derivative of sine is cosine. Okay, so we're going to do a little bit of kind of tough work here to sort of prove that that's true. We're going to use this fact to extrapolate all of the other trig derivatives. So I kind of don't want to let you off the hook and just be like, it is, take my word for it. I mean, I could be lying, right? So we are going to use the definition to try to show this, foundationally that this is true. And we're going to skip over a little bit. So we're going to get a little into the weeds with some algebra here, but it's for a good cause, so stay with me. So here's the setup. The limit as h goes to 0 of sine of x plus h minus sine of x over h. Sine of x plus h, that doesn't split up into sine of x plus sine of h. There's no way to factor the top. There's no way to conjugate it. Here's what you do. So you're all out there going, oh, that's the addition identity for sine. It's sine of x times cosine of h plus cosine of x times sine of h. I would be shocked if you actually remembered that formula. I would never make you memorize those formulas from trig, but you did see it. You absolutely saw it in trig class. Probably towards the end, that was one of those identities you saw. So that's the addition identity for sine. I'm not going to say why it works. It just does. It's out there for us to use. So that's how we have to split up that sine of x plus h. So here we go. That turns into, okay, sine of x times cosine of h plus cosine of x times sine of h. And then that minus sine of x on the end. This next move, you're kind of going to wonder why I'm doing it, but just bear with me. I'm just going to take that last term and stick it in the middle. So all I did there was just took the minus sine x that was on the end and stuck it in the middle. And then that middle term goes to the end. And the reason I did that is so I can factor something out of the first two terms. Again, if you're wondering why, just bear with me. You'll see. So now I have the common factor of sine of x between the first two terms, so I'm going to take it out. So we're left over with cosine of h minus 1 when we do that factoring. We now have a bunch of stuff in the numerator that's just over one thing in the denominator. So we can do our familiar move where we split that into two fractions. That's just the laws of fractions. So there's no calculus happening here. This is just using algebra to move stuff around and one trig identity. Okay, so we're allowed to do that. We're allowed to split it up into two fractions that have that common denominator of h. We're then allowed to split that into two limits just because of the old limit law we had where I said, okay, the limit of a sum is the same thing as the sum of the limits. So that behaves nicely and just splits up into two things that we can look at separately. So we're going to examine those two things as separate limits. The first thing is just to say that this first term here inside the limit is sine of x times cosine of h minus 1 over h. The part of that that's just sine of x isn't affected at all by h going to 0. You can really just think about that as a constant. Same as the cosine of x in that second limit. That is not affected by what's happening with h. So given that, we can just treat it like a constant and just pull it outside of the limit. It doesn't affect anything. So that's what that looks like. So we're pulling things outside of the limit that the limit doesn't affect. The limit only affects the stuff with the h's in it. And that's kind of why we factored that sine out, so that we could pull it outside. And the cosine comes out as well. Okay, we're almost there, I promise. So here's the part where I'm going to cheat a little bit. We have two limits here. One of them is the limit of cosine of h minus 1 over h. Remember that cosine of 0 is 1, so that limit is 0 over 0. We can't just plug it in. And then we have the limit of sine of h over h. Sine of 0 is 0, so that we don't really know that either. We saw the very first limit we actually ever saw in this class was sine of x over x, and we looked at what happened when x was near 0, and we saw that this function went to 1. So this is the part where I mean we're not going to go all the way. So I'm going to tell you that the limit of that first thing is 0. Go ahead and graph cosine of x minus 1 over x if you don't believe me. It looks like it goes right through the origin, even though there's a hole at 0. And then the same with that second limit, it goes right through the point 1. So there's a hole at 0, 1. To actually prove either of those facts is hard, and we're not going to do it. So look at the graphs if you don't believe me, or just believe me because I know what I'm talking about. Okay, so that first limit just becomes 0, which means that first term drops out. That second limit is 1. So that whole thing turns into sine of x times 0 plus cosine of x times 1, which is just cosine of x. Okay, so that was us like eating our vegetables so we could like have our dessert. We're not going to do that with all 6 trig functions. We're just going to use this one fact to get the other ones. And now we've done the work to say, okay, that seems right. It already seemed like the derivative of sine was cosine. Now we've seen some work to say that, okay, it is after all. So it would be really nice. So that's another derivative. There you go. Put it up on the board. It would be really nice if the derivative of cosine was sine, but it's not. So we could do all the same moves, or we could use the graph. If you look at the graph of cosine and think about what its derivative should look like, it looks like an upside down sign. So for however you have to memorize it, the derivative of sine is cosine. The derivative of cosine is negative sine. It's an upside down sine function. That's just what it is. Soon we'll put them all in one place. Let's just go through a couple more. Obviously, we want to do stuff with this. Right now, while we're in it, let's just get a couple more trig derivatives. So to get the derivative of tangent, I'm not going to make us do like the definitional with like the tangent of x plus h. Then you need an addition identity for tangent, but don't want to do that. But we can just use the quotient rule. And the reason we can use the quotient rule is because every single one of you remembers from trig class that tangent is sine over cosine, right? That's the definition of tangent. That's the kind of thing I do expect you to remember from trig class, is definitions. I don't expect you to remember all those weird formulas and identities, but I expect you to remember what tangent, what it even is. So we just write it as sine over cosine, and now we can use the quotient rule on that and see what we get, see what it cleans up to. All right, so that's cosine times the derivative of sine minus sine times the derivative of cosine all over the denominator squared, so all over cosine squared. The derivative of sine is cosine. The derivative of cosine is negative sine. So that's it. That's the derivative of tangent, but we're going to make it look prettier than that. Cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared. And cosine squared plus sine squared, this is one of the only other things I expect you to remember from trig class, should be really ringing a bell, because cosine squared plus sine squared is always equal to 1, right? No matter what. That's a universal identity for any x, and it's what I call the fundamental identity of trig. So that is never going to go away. Okay, so this is it. It's 1 over cosine squared, but we don't leave it like that. It's just one of those conventions of math. So instead of writing 1 over cosine squared, we're going to write this as 1 over cosine squared. If that makes sense, right? And then we're going to say, okay, of course you remember that 1 over cosine is the same thing as secant. So that just simplifies to secant squared. So the derivative of tangent is secant squared. There's another one. Again, we'll summarize at the end. But now we have a derivative for the tangent function. It's the secant function squared. Let's compare those graphs just to make sure it jibes with what we know about functions and their derivatives. Remember, the tangent function is a graph that has a lot of vertical asymptotes, and it's just a bunch of arcs that like shoot up between them. So the green curve is tangent, and the red curve is its derivative. Notice the tangent function is increasing everywhere, which means its derivative better be positive everywhere. And it sure looks like the red graph is. In fact, it's secant squared, so any number squared is positive, so that works out. So at tangent's vertical asymptotes, at all those pi over 2's, right? Pi over 2, 3 pi over 2, it shoots up really fast to infinity, which means the derivative should get really big as well. So that works. So the secant function also has asymptotes at all those same exact locations. Okay, we'll do one more, and then I'm going to leave the other two, I think, to you on some quiz or another. We're going to use the quotient rule again to find the derivative of secant. We don't need to do it by definition. We did that with sine. And we're just going to rewrite it as 1 over cosine, which is the definition of secant, right? That's one of the things you should remember from trig class. So the derivative of 1 over cosine, using the quotient rule, is, right, so we actually already did an exercise where we had the derivative of 1 over a function. So I'm kind of skipping ahead. So it's Cosine of x times the derivative of 1, which is 0, minus 1 times the derivative of cosine. So all that simplifies to just minus derivative of cosine. So I don't expect you to memorize stuff like that, but that's why we have why we say, okay, in general, this always happens, so then we can use that stuff later, because 1 over a function is something we see a lot. So it's just negative derivative of cosine over cosine squared. That's just the quotient rule. The derivative of cosine is negative sine, so negative sine is sine. So that's it, but that's not how you're going to see it at all. You wouldn't know that. This is just what we do. So we use some trig stuff to rewrite it. So we're going to rewrite that as 1 over cosine times sine over cosine, right? Convince yourself that that's an okay move. 1 over cosine is secant. Sine over cosine is tangent. So that's how you're going to see it, and that's the rule you're going to remember and memorize. The derivative of secant is itself times tangent. That's kind of new. We haven't really seen a function whose derivative had a copy of itself in it. This one does. So that's just how it is. The derivative of secant is secant times tangent. So it's also like two functions. The derivative of this one function is a product of two functions. Cosecant and cotangent, you can handle. I'm sure I'm going to make you do one of those at some point. So it's the same methods. Use the quotient rule. Let's just put them all in one place, though, just so we, summarize. There they are. So if you ever had to memorize these, which most calculus students do, here's how I kind of organize it. So you just kind of remember the derivative of sine is cosine and the derivative of cosine is negative sine. You just remember them, however. And then you also remember the derivative of tangent is secant squared. And you also remember that the derivative of secant is itself times tangent. Notice the derivative of cotangent is negative cosecant squared. So it's like the derivative of tangent, except it's just the other thing, cosecant, and it's negative. And then the derivative of cosecant is a lot like the derivative of secant, except it's negative itself times cotangent. So you would first just remember that, okay, all the co-ones, the co-functions, cosine, cotangent, cosecant, they all have negative derivatives. So just however you remember that. And then if you remember that the derivative of tangent is secant squared, that should be your cue to remember that the derivative of cotangent is negative cosecant squared. It's negative because it's co, and it's negative the other one squared. And then the derivative of cosecant is negative itself times cotangent, just like the derivative of secant is positive itself times tangent. So there they are. That's pretty good progress. If you remember, there are also 6 inverse trig functions, but we'll get to those later. We will figure out their derivatives. But now we have all of our trig stuff. And now we can actually do stuff like with the product rule and the quotient rule, where it comes in handy and we can mix and match different types of functions. I wanted to do one kind of velocity-ish example first, so it's easy to forget what this stuff is. So I want to remind you what it is. So simple harmonic motion is when something just goes up and down in a very regular fashion. So we pull down a mass on the end of a spring and we let it go, and we just say that it moves in the absolute simplest of harmonic motion, which means it moves up and down exactly like a sine wave or a cosine wave does. So here's a graph of what that looks like over time. So it starts at the bottom and then goes to the top and then comes back down. So what is that the graph of? That's an upside down cosine wave, right? Cosine is the one that starts at the top of its wave. This one is just flipped upside down. So that's negative cosine of t. So it's what we call displacement at time t is given by negative cosine of t, or just the graph you see in front of you. We want to look at what's going on with this thing's velocity and its acceleration. And in particular, when you remember with velocity, velocity has direction. So positive velocity corresponds with the mass moving up, and negative velocity corresponds with the mass moving down. So you can kind of get a sense of what it should look like before we even do the math. But we have derivatives for this stuff now, so we can do the math. So velocity is the derivative of displacement. So the derivative of negative cosine is negative sine, or just sine, right? So the derivative of negative cosine is sine. So its velocity at any time, at least between 0 and 2 pi here, is just given by the sine of t. And then acceleration, you just go one step further. So that's f double prime. So the derivative of sine is cosine. So velocity is sine of t, acceleration is just cosine of t. You see how these derivatives are like cyclic? If you keep going, you get it back. But this is as far as we need to go. So I'm going to put a table up here that has its velocity and acceleration for this whole time period you see charted. There's going to be a bunch of numbers, but we'll walk through them. Okay, so just start at the first row. S of t, that's the displacement, starts at the bottom at -1, goes up, square root of 2 over 2 is about 0.7. Goes up to 0, goes up to 1, and then comes back down again. So that's just that's just wave-like behavior. If you look at the velocity, so that second row there, v of t, the velocity right at the beginning is 0 because it's essentially at the end of its motion. And then it speeds up. So at time pi over 4, it's at square root of 2 over 2. At time pi over 2, it's 1. So that's actually, if you look at those velocities, that's the fastest it's ever going. So the fastest it's going is right in the middle of its path, because that's where it switches from speeding up, right? It's speeding up towards the middle, and then it starts slowing down again so that it can stop at the top. So if you think about the moment you switch from speeding up to slowing down, that's like the fastest you're going in that little area. So right at pi over 2 and 3 pi over 2 is the fastest the mass is traveling. So right then it starts to slow down again in a very symmetrical way. At 3 pi over 4, it's back down to 0.7. At pi, it's stopped, right? So at the moment when it's turning around, when it's at the very top of its peak, so it's switching from going up to going down, the velocity is 0. Right? Because it is essentially stopped at that little discrete moment in time. It then speeds up again in the other direction, right? So now it's going -0.7 because it's going down. And at 3 pi over 2, it's going -1 because it's traveling down as fast as it's going. It then slows down again to negative square root of 2 over 2 so that it can stop again at 2 pi, and now the velocity is 0 again. Okay, so those should make sense. Acceleration is a little more confusing. It's not as simple as you might think. In other words, if acceleration is big, you're going fast. That's not how it works, because acceleration also has direction. So at time t equals 0, the acceleration is 1. And notice that's the biggest that ever gets. So this is just cosine of those numbers. The most it's ever accelerating is 1, and it's at those moments. Because you can think about that's when the spring, when it's all the way pulled down, has the most like upward like potential energy. Like it's being pulled as much as it's ever going to be pulled in the upwards direction. So if you look at square root of 2 over 2, it's still accelerating up because acceleration is positive. Right? And then if you go over to pi over 2, where the spring is right in the middle, the acceleration is 0. Because what's happening there is the spring is switching from speeding up to slowing down, right? So right after that, subsequently at 3 pi over 4, the acceleration becomes negative, because now it's like while the spring is traveling up, it has to slow down. So the spring's traveling up, the acceleration is negative, pulling down, that means it's slowing down. And in general, that's what we see. Anytime velocity and acceleration have opposite signs, like one's positive, one's negative, our object is slowing down. If they have the same sign, then our object is speeding up. So if you look at pi, where the velocity is 0, now the acceleration is very big negative, is -1. So that's when it's being pulled down as much as it's ever going to be, right? That's when the spring really wants to be going down, because that's the way the acceleration is pulling it. So then it keeps going down, acceleration is still negative, but it's less. And if you look at 3 pi over 2, acceleration is 0, because that's the moment when the spring is going down, but it switches to speeding up in the downward direction. So at 7 pi over 4, the spring's going down and the acceleration is pulling down. So that means it's speeding up that way, right? And then at 2 pi, the acceleration is 1 again, because once again the spring's being pulled in the upwards direction because it's all the way at the bottom. Whew. Okay, let me summarize what I just said. All right, so in a displacement function, velocity is positive if we're going up, negative if we're going down. Velocity is only ever 0 at a moment when it changes directions, unless it just stopped and kept going. So like if you stopped at a stop sign in your car and just kept going, yeah, your velocity was 0. If you stopped at a stop sign in your car, put it in reverse and went backwards, then your velocity was also 0 at that moment, but you probably don't do that as much. Right, so anytime it's to the top or the bottom, it has 0 velocity. Acceleration is only ever positive if it's speeding up in the positive, if it's going up and speeding up, or going down and speeding up, right? So acceleration would be negative if it was going down and speeding up. So, right, positive acceleration is pulling the spring up, negative acceleration is pulling the spring down. And depending on which direction the thing's actually going, that's going to either speed it up or slow it down. They have to be pulling the same way to speed the thing up. Okay, so let's just do some derivatives. We're getting closer to the kind of stuff you're going to have to do on this next exam, which is derivatives that are just hard for the sake of being hard. That's just how we do it. We just throw a bunch of stuff at you and be like, okay, if you can do this, you can do whatever. So we'll build it up a little bit. So this is the derivative of x squared times sine of x. This is the first time we've actually really needed to use the product rule. We've said up to now you can always kind of get away with not using it because you can combine things algebraically, but you can't combine x squared and sine of x algebraically, right? This just is that. There's nothing you can do with that, so you have to use the product rule. So it's pretty simple. So it's the first function times the derivative of the second function, so x squared times the derivative of sine, plus the derivative of x squared times sine. It's that easy. So when you use the product rule, you're usually always going to have 2 terms in your answer. So that's it. You're done. It's x squared times cosine of x plus 2x times sine of x. And a complicated function, x squared sine x, if you looked at the graph of that, it's a pretty complicated function. So complicated functions generally have more complicated derivatives, right? Because it's doing a lot of weird up and down stuff. So the derivative has to compensate for all that up and down type of stuff. And the fact that it's based on 2 separate things, a squaring function and a trig function. So that's it. There's no way to simplify that. That's what it is. That's our derivative. Easy. This isn't hard either. At the moment, if you want to do the derivative of a function squared, you would just use the product rule. Next, we get a rule called the chain rule that you could also use, and you'd get the same thing. But let's do it with the product rule. So remember what sine squared means. It means sine of x squared, which means sine of x times sine of x. So to use the product rule on something like this, you would just split it up like that. Right? So now it's product rule. It's just f and g are the same function. So the derivative of sine of x times sine of x is sine of x times the derivative of sine of x plus the derivative of sine of x times sine of x. Right? That's just the product rule. It's just that both functions just happen to be the same function. Okay, so those are both the same term. We get sine of x times cosine of x plus cosine of x times sine of x. Since that's the same thing, there's absolutely no reason not to combine it into one term. So that's just 2 times sine of x times cosine of x. And you can kind of see that that'll always happen. Right? If you have the derivative of a function times itself or a function squared, the product rule is going to give you the same term both times, so it's just going to be 2 times whatever that term is. And in particular, it's 2 times the function times the derivative of the function. So we have another mini formula here. So again, this isn't like a new formula you have to memorize. It's just a pattern. It's just a trend. Just notice that every time we use the product rule on a function times itself or a function squared, so in trig you do see a lot of functions squared. You see tan squared and secant squared, and right? We get the same thing. So the derivative of a function squared is just 2 times the function times its derivative always. Okay, so now we're getting a little uglier. This is more like the kind of thing you're going to see on the exam, where we have to use a lot of rules in one derivative. So this is going to get pretty ugly. This is going to be some of the uglier math you've ever done. It's going to get even worse soon. But it's not, I don't think this is hard. It's just, you have to stay organized and your answer is hideous. That's it. This isn't the hardest math you've done. So this is a quotient, except that the numerator is a product. So when we do the derivative of the numerator, we have to use the product rule inside of the quotient rule to get that. Fun. Okay, so here we go. It's the bottom times the derivative of the top, so tangent of x times the derivative of x cubed times secant of x, minus the top times the derivative of the bottom, so x cubed secant of x times the derivative of tangent, all over the bottom squared. And for that first term in the numerator, we have to use the product rule to get the derivative of x cubed times secant of x. We have tangent of x times, all in brackets, now we're using the product rule. So it's x cubed times the derivative of secant plus the derivative of x cubed times secant minus, so we did the differentiation on this part. X cubed times secant of x, the derivative of tangent is secant squared, right? So again, it's ugly. But if you just stay organized, it's just one thing at a time. And all you're doing is just using the derivative rules. You just have to be careful about how you're using them and just doing it step by step. Okay, so I just copied that. That's just the last line. That first line here is just the last line from the last slide. So now we're just going to do the product rule on that thing in the brackets there. So it's tangent of x times x cubed. It looks weird, but the derivative of secant is itself times tangent. So it's x cubed times secant of x times tangent of x plus 3x squared, right? That's the derivative of x cubed times secant of x. And then minus, so I've always said you don't have to simplify stuff. To me, if you have a secant times a secant squared, there's no reason not to write it just as secant cubed. But if you didn't, I wouldn't mark it wrong. So sometimes I'll do a little bit of common sense simplification just because it looks weird to me not to. But like in the instructions on the next test and stuff, it'll say like you don't have to simplify your answers, right? So as long as you do all the differentiation and get it to there, you're good. Okay, and then this is fine. You could distribute that thing in the brackets in the numerator. If you split this into 2 fractions, you could probably simplify it. If you rewrote some trig stuff, maybe you could simplify it. But why? Why do any of that stuff? It's not like we're going to graph this or solve it or anything. It's just a big ugly answer. So this is totally fine. I would prefer if you just left it like this. And right, you see what I mean about this it's almost not hard. It's almost not even math. It's just kind of putting stuff where it goes. It's just turning stuff into other stuff and remembering where it goes. So it's not like the kind of algebra you've done before where you have to solve an equation that's hard. It's just kind of rewriting and using a bunch of new rules. And I know it looks hideous, but you'll see. The more we do this, like it looks a lot harder than it is. Okay, so again, just kind of throwing them. This is just hard for the sake of hard. right? There's no application here. I'm just making you do hard derivatives. So we now have the product of three functions, x squared times cosecant times cotangent. Oh boy. So we have to use the product rule on it, but we have to use it twice. So what we're going to do is we're going to consider this a product of two functions. It's just that one of them happens to also be a product. So if we consider this like f of x is x squared and g of x is cosecant times cotangent. That seems to make the most sense to me because cosecant and cotangent are the same kind of function. So you don't have to do it this way. It would work out the same no matter which you picked. But for right now, when we're applying the product rule, let's let the x squared be the first function and the cosecant times the cotangent be the second function. Here we go. Okay, so the product rule says it's the first times the derivative of the second, so x squared times the derivative of cosecant times cotangent, plus the derivative of the first times the second. So the derivative of x squared times cosecant times cotangent. That second term is easy. We know the derivative of x squared. The first term is where, great, now we have to use the product rule again. So now cosecant is our f and cotangent is our g. So we use the product rule in those brackets in that first term. So that expands to the first times the derivative of the second, cosecant times the derivative of cotangent, plus the derivative of the first times the second. So derivative of cosecant times cotangent. I'm really going overboard with parentheses because I always say too many parentheses is fine. Your book probably isn't as careful as I am. I just want to make sure you know what you're doing the derivative of. And in the second term, we just went ahead and did it. We just did the differentiation. That second term is done. It's just 2x times cosecant of x times cotangent of x. Okay, so just working inside of those brackets now, it's cosecant of x times the derivative of cotangent is negative cosecant squared, plus the derivative of cosecant, which is negative itself times cotangent, times the second, which is cotangent. All right, and then plus that last term, which is already dealt with. Okay, so again, if you left it here, I wouldn't mark it wrong. All right, so it's ugly, but you could leave it right here. To me, again, it's just kind of common sense to, okay, if you have cosecant times cosecant squared, negative cosecant squared, why not just call that negative cosecant cubed? To me, it just looks unresolved to leave it like that. So that first term is negative cosecant cubed, and that second term, okay, we have two cotangents, so it's minus cosecant times cotangent squared. That to me is, again, a common sense simplification. You could then take it one step further, multiply that x squared into everything and just get rid of parentheses, but I'm not gonna because, again, this is the answer. So, right, if you just saw this and didn't know what we were doing, you'd be like, oh my god, that's impossible math. What is that stuff? But once you know what we're doing, like I said, it's almost not even really algebra. You're just putting stuff in its right place. Okay, so that's the kind of derivative we're going to get into going forward. And the focus in the next test really is just on purposefully hard derivatives, just to force you to really master these rules.